It was so dumb.
Because
Okay.
testosterone.
When more than one man is gathered together, the action goes down. Proportionately to the amount of men
I watched.
together.
Yeah, you gotta be really low here.
It's actually like putting resistors in parallel.
Why do you ask?
As
It's
my
never bigger than the smallest value.
As my aunt said, one guy, one brain. Two guys, half brains. Three guys, no brains. Any girls, no brains. Like girls with guys that want to rack themselves pretty bad.
Girls without guys.
Girls,
Girls, no thanks.
Well, I'm thinking of the guys have no brains as a girl.
Okay.
nice little room though.
Last one today. This is it. The last material science lecture of the semester. We'll see how far we make it. If I can get Daniel to quiet himself. And perhaps get Cassidy and Clayton's attention.
I am listening.
You were chatting! And now Joel and Clay,
It's called multitasking.
everybody's talking to each other. No, you weren't. Wednesday, we'll have no class. There's no class on Wednesday because general physics, I have to go give them their exam and I can't get anybody else to proctor it. So we'll have no class on Wednesday, and then there will be the opportunity for you to ask questions in preparation for the final on Friday. So if you do not prepare questions to ask me, then there will be nothing to discuss on Friday.
We're not doing a review project.
We're not doing that, no, because it really doesn't have the same value in material science as it does in thermal. So, but again, if you have questions, materials questions you'd like to go over, it would be helpful if you could email them to me Thursday afternoon so that I know what we'll be discussing on Friday. Yes,
Is the final exam still Wednesday from 1 to 3?
it is whenever it was scheduled.
I think it might be Monday.
Yeah, it's Monday. It's Monday.
Monday?
Thermal is Monday.
So that means we have
Yeah.
materials and then the end question.
It's whenever it was scheduled. The 14th, whatever the 14th is. Is that Monday? It's the 14th at 10 a.m. Because that's when all the homework is due. The homework, you know, like you know how I let you have a second shot at the homework? All the homework has to be done the moment the final starts. Same is true in thermal for those of you with thermal. Yes, ma'am.
Will you post some sort of study guide like you have?
So it would only be for the electrical part, because the study guide for the other parts is going to be basically the same. It's a comprehensive test. So yes, if I remember and have time to pull it together, I will.
Are we?
Yeah, his hand in
Will we have the opportunity to like look at our old tests and study from those?
here. Yes. Okay. So on the exams for the first couple times through, I'm trying. I don't know why you bother like sneaking.
Oh, crap.
And then you have to pick up off the floor, your hands are gonna have to get dirty. Oh well.
You, Clay.
Oh, you big. Oh, gross, that's even harder. That's better.
Oh my
Oh.
For those of you watching at home, Clayton just picked up a dirty tissue to pick up a little piece of banana on the floor.
Anyway.
They're all a bunch of peanuts.
So you can have them to study, but you have to give them back to me when you're done. I still haven't turned them in to next door. I rushed to get them graded and then I completely forget about them. So I still haven't made the ABAC copies yet. So if you stop by my office, you can have them back, but then I'll still need them back after that. Yes.
Are you doing the ABET evaluation things? Do we need to do the ABET evaluation course for surveys, coursing surveys? You know me and terms. I don't get along well with them.
Daniel and words are having an argument. Honestly, I think that one's correct. I think you can do that. I think that one's been updated. So I think you can if you want to. I don't know if they've been released or not. Have they?
We haven't heard anything about it. I wonder if we were supposed to hear about it.
It's Dr. Geisler who's in charge of that.
Okay.
So, but the thing is, every year we're supposed to make sure that the questions are up to date and everything. So I had to go through that process the last time I taught the class in order to make sure that it's up to date. Okay, any other questions?
I have
Yes.
a question, just to make the last class kind of interesting. Can we do like an extra credit offering where we all put a number in a hat? And then the closest to the total amount of questions asked by these two, and at the end of the period, gets like 2% extra credit in the course or something
No,
like that?
no.
Created by 2%.
It'd be kind of fun, I don't know. Monitor, like, over under 30 total questions.
No, because you know that both of them would say, they would collude, and they would both put 0 in, and then, you know, tape their mouth shut, so.
I don't think it's physically possible.
Yeah.
Yeah, that's,
They don't have the will.
Any other questions, perhaps of a more serious note?
Actually, you
Yes.
could probably just bring up swords or something and they couldn't handle
That's a good point.
You mean just that?
Anyway. Any other questions? Okay. 42, that's right. All right, any other concerns or thoughts or whatever otherwise unrelated to the coming? No? Okay, then let's finish. Let's move on to these. Basically, all we're going through now, this is the only thing we have left. We've talked about semiconductors. So now we're going to discuss the various devices that we can make from those semiconductors. And we're going to have, let's see here, hold on a second. Okay. So the first kind of semiconductor device we had were, first kind of semiconductor material we had was intrinsic semiconductor. So we have a few intrinsic semiconductor devices as well. Examples of this would be photodetector. Oh, and I should have mentioned too, in the intrinsic materials, like I listed silicon as an intrinsic material, as an intrinsic semiconductor material. And generally, if you look in your table of, in your group 4 materials, you'll find that they are all intrinsic semiconductors. So silicon is an intrinsic semiconductor, germanium is an intrinsic semiconductor, and actually if you look below that, tin, one of the forms of tin is actually a semiconductor. Okay, one's a metal, but one's an intrinsic semiconductor. But you can also get an intrinsic semiconductor by mixing equally 3 and 5 group materials. So I can mix equal portions of gallium and arsenic and get gallium arsenide, which is an intrinsic semiconductor. So even though it has 2 materials, gallium and arsenic, it is not a doped semiconductor. Everybody understand that?
So, in order to be doped, there would have to be a small amount of those? Is that the idea?
Right, so a dopant is like silicon with a little bit of phosphorus or a little bit of boron, right? Now, and indium antimonide, so if you go down below below that in the table, indium and antimony is another 3,5 semiconductor. They are intrinsic semiconductors. They are not they're not doped. Okay, so photodetectors, photoluminescence is another one. Photoluminescence, examples of intrinsic devices.
Would that be like an LED?
What's that?
That's an LED.
Like an LED. Right. So the gap energy in silicon is on the order of 1.1 electron volts. That's the size of that gap. Right, from valence band to conduction band in pure silicon. So what happens is, if I have a photon that comes in, and it's a red photon, just a simple red photon, right? So the wavelength of red is, let's say, 660 nanometers. Those LED laser pointers are 650, so it's about that gigahertz. But 660 for some reason is what I had wrote down here. That has an energy of 1.9 electron volts. H nu. To get the energy. So 1.9 electron volts is enough energy, if it's absorbed by an electron in the valence band, to kick that electron from the valence band up into the conduction band and allow conduction to occur. Or at least one electron's worth of conduction. So, as a result, it can serve as a photodetector, where the amount of, the number of electrons coming through, the amount of charge, the amount of current passing from the photodetector device is going to be proportional to the number of wavelengths, or number of photons, at an energy sufficient to cause excitation. Now, obviously, green and blue would have even higher energies, right? They have higher frequencies, shorter wavelengths, and therefore they'd also be able to excite conduction in silicon. Okay, so we'd be counting total all photons. And the similar thing can happen in reverse. So the LED is the same thing happening in reverse. We'll talk about diodes in a second. So anyway, and basically what that means then is that sigma goes up as the, sigma goes up as these things are impinging. So the resistivity goes down, so that the resistance goes down. So the current goes up for a particular voltage. I can see it. Okay. So that's what happens if I've got a potential there to excite that electron to move through the conduction band. If there's, that's kind of, I guess. If there is no potential, right, so that electron's excited up the conduction band but doesn't have any motivation for going anywhere, then it will eventually decay back. So, if you look at the energy structure here, this is the valence band, this is the conduction band, right? So, if I take this electron and excite it with red light, I actually excite it up to here. Remember, this is only 1.1, so I excite it by 1.9, right? It can thermally decay down to here. I can lose some energy through thermal processes, just collisions with other electrons, whatever. But it can't get back down to here unless it does so in a quantum effect of releasing a wavelength, releasing a photon. That make sense? Okay. And in this case, if it actually did this jump, that would be an infrared photon. Because red is 1.9. A lower energy is going to be an infrared photon. So it would release an infrared photon if it were excited like that in silicon. Okay?
What's an electron volt?
An electron volt is 1.6 times 10 to the minus 16 joules. It's one electron, because of joule is an amp volt. Remember that? No. Okay. So, an amp times a volt, actually an amp volt is a watt, but anyway. It's a watt because amps is per second. So a coulomb volt is a joule, right? So an electron volt just uses the charge of an electron instead of a coulomb. So it's 1.6 times 10 to the minus 19 joules for 1 electron volt. So it's just a unit of energy, but it's one that's more useful when we're talking about electrons. Okay, so I excited it up at a higher, what I typically get out is going to be something at a slightly shorter, lower energy, longer wavelength. Okay? So the example there is, and actually what happens is it's the combination of an electron hole pair, right? We have an electron up here, and there's a hole down here, and those two recombine. Have you guys were ever, when you were little kids? I know when I was a little kid, I used to, I had a little cross, a little plastic cross, glow-in-the-dark cross. You guys have little plastic glow-in-the-dark somethings when you were a little kid, right? I used to love it. I leave it hanging on the lamp next to my bed, and then at bedtime, you know, Mom would turn out the lights, and I'd grab the little cross and go into the covers, and I could still see, you know, what I'm talking about, right? We've all had this experience. All right, so that's photoluminescence, right? What happened there was I had the long wavelength, or the short wavelength, the high energy electron or photons from the lamp charging these electrons, exciting these electrons inside my little piece of glow-in-the-dark plastic. And then when we turn off the lights, the glow-in-the-dark plastic glows with a color that's corresponding to some particular energy gap. So it glows with a green or whatever, that's the energy gap. And glow sticks, those glow sticks, right? Break them, there's a chemical reaction and they glow. Well, what's happening there, again, same thing, the chemical reaction excites the electrons, and then the release of those electrons back to the lower energy state emits a photon in proportion to the amount of energy for the gap. All right. So that's another way of exciting them. So here we've excited them with a photon, and they decay back with a photon. You can also excite them with chemical energy in a glow stick. You can excite them with electrical energy. You can actually bombard the phosphors in, we're going really old school now, but in an old television screen, right? You know, like the CRTs, cathode ray tubes, right? The reason they glow is because there's a beam of electrons coming out there. The electrons themselves collide with the electrons in the phosphor and pump them to higher energy through translational kinetic energy as the incoming photon hits that thing, pumps it up to a higher energy, and then as it decays back down, it emits a photon of a particular color. So if I hit the green photon, or the green phosphors with an electron beam, then it glows green because the gap energy is just such that green is the light that's emitted. Okay, are you guys familiar with this? Am I just sort of, I don't need to be talking about it then? He's being difficult now.
No. I'm literally like, you just said it's like a green.
Right, so the phosphorus in a color television set, if you get a magnifying glass, look at the color television set, red dot, green dot, blue dot, red dot, green dot, blue dot.
So is that
Red,
just
green, and
like
blue dots.
a colored material, or is that like a...
It's a phosphorus, they're just chemically different material. What's in here are those same phosphors.
So the phosphorus...
These things are not white. These are the combination, simultaneous combination of deep blue, cyan, yellow, green, and red.
Okay. So,
5 colors coming from these lamps, 5 different phosphors.
So are those phosphors like different isotopes of phosphor?
Yeah, they're not phosphorus.
Oh.
Phosphorus, actually, they're called phosphorus because because phosphorus behaves this way. But that is not what they are. They're
Okay,
not
so
phosphorus,
they're each like
phosphorus.
a different material.
Right, exactly.
Okay, that makes a lot more sense.
And you can also use this then as a thermistor. Okay, you can use these things as a thermistor because conductivity is proportional to the temperature, right? We showed before. Right, some kind of energy here, depending on the nature of the semiconductor, right? There's Eg over 2 for an intrinsic semiconductor. Anyway, the point is, there's a temperature dependence for conductivity. So you can measure temperature that way. You measure the conductivity and correlate it back to the actual temperature of the device, thermistor. So we have photodetectors, photoluminescents, thermistors. I think that's everything. All right, those are good uses for intrinsic semiconductors, but most semiconductor applications involve extrinsic semiconductors. So the ones we're really going to focus on now for the rest of the time are going to be extrinsic devices. Also known as outrinsic devices. So the first of these is, junction devices is a diode. So here we have two types. We have an N-type and a P-type semiconductor, and they're put in physical contact. So the P-type has a bunch of electron holes. Right, we've already talked about the difference between N-type and P-type, right? Everybody remembers? Depends on what the charge carrier is. And the N-type has a bunch of electrons. That have all been thermally excited. Right? Okay. If I put a battery on here, right? Put the positive side over here, negative side over there, what's going to happen? What's going to happen to all these electrons?
The negative ones will go where positive ones are, and positive ones.
What's going to happen to these negative electrons?
They're gonna be attracted down.
To the positive.
Or,
Oh, yeah.
What direction are they going to move, left or right?
Left.
They're going to move left, right? They're going to move toward this positive terminal. And these holes are going to move where?
Right.
To the right, right? Okay, so I'm going to collect all my electrons over here on the left, and collect all my holes over there on the right. Okay, but they're not actually able to go anywhere. I can't create more electrons. Right? I'm not going to get any more electrons moving through the system. You see what I'm saying? So what I end up doing in that configuration is essentially concentrating all of my charge carriers out of the sides. Right? They're all there. And then my holes are all over here. And I get no conduction. Right? No? You disagree?
I was like asking a question.
Was it materials related question?
It was.
Anyway, does that make sense? The charge carriers move over here, there's nothing to,
If you were to cut that in half, somehow, would you end up with like a negatively charged piece and a positively charged piece at that point?
so it already was a negatively charged piece and a positively charged piece
So those are two separate pieces of material.
that are put in electrical conduct.
Oh, okay.
Connection. They're in contact, electrical contact. They're placed in electrical contact. Okay. Two different materials. Actually, it could be silicon, one half of which is doped with boron and one which is doped with phosphorus, right? I can dope it, take one chunk and dope it two different ways in the two different regions. But the point is, this is what ends up happening. Okay. Now, if I polarize it the opposite direction, then what's going to happen to all my electron holes? What's that? Yeah, they're going to go left, right? And they're eventually going to meet at the center. All of the electrons that are moving to the right. And they're going to annihilate one another. Right? So this electron is going to move to the right, electron hole is going to move to the left, they're going to meet An electron's gonna fill that electron hole. So now I have one too few electrons over here. Right? So I'm gonna be able to pump another one in. And I have one too few holes over here, so I'm gonna pump an electron out to create another hole. So every time I have an annihilation event, I'm gonna be able to bring in another electron or a hole from the outside source. Does that make sense? So now I have forward bias here that allows conduction to occur at a much higher rate than over here when I have reverse bias. Now, it turns out, even in reverse bias, there's still some conductivity. Because even though there are predominantly negative charge carriers here, at room temperature, we know there are still some holes over here. Right? We saw on the Fermi diagram, right? At room temperature, there's still a few holes created in an N-type. And there are a few electrons pumped up to the conduction band in a P-type semiconductor. So there is still some intrinsic conductivity. But it's much lower than the extrinsic conductivity, if you remember from the graph. Right? Remember the graph that did something like this? Right? The graph did this, and then there was the saturation range, and there was that, right? So at any particular temperature, there's a dramatically higher conductivity due to the extrinsic behavior than there would be due to the intrinsic behavior. So there's always a little bit of current flow into reverse bias. Everybody familiar with that in regular diodes? We should have talked about that in circuits. Yeah.
So what happens in the breakdown then? Does that when it breaks it all the way up and over so that it's acting just as intrinsic? Or
So what happens here is basically there's the, yeah, let me erase that, the avalanche. Okay, and what we call this, I should put one more word up here, hold on. This section, center section here is called the depletion zone. Okay? So what happens is, as I have the behavior does this on the positive side, and down here, and then the avalanche region at the back end. You guys call that avalanche? I mean, that's what I always call it. Is there
the
another-
breakdown?
Breakdown? Okay, I call it avalanche. Okay. So what happens is, this is a really positive charge over here. There's a really strong positive charge over here. So, excuse me, the electrons that are, what happens is you essentially have really high velocities for the charges that do remain in this depletion zone. And effectively what you have is you have some electrons that move, so if the holes move over here, the electrons move to this side, right? But there's no place for them to go over here. See what I'm saying? So there are still electrons in this section that move that direction. When the holes move to the right, it's really the electrons that are moving to the left. Does that make sense? Well, those electrons, if it's a high enough voltage, those electrons are imparted with enough velocity that they literally cross that region. They have enough momentum to cross that region. And then they make it over there, and the whole thing conducts in that direction. Well, the current electrons go in that direction, current flows the other way, you know what I mean? So essentially what happens is on this side, the electrons are excited beyond the, with enough momentum or enough energy to make it through this zone. Now, if you make this wider, then the breakdown voltage goes higher, or lower, whichever way you look at it. Okay. But these are typically, sub-micron scale devices, right? They're typically small scale devices. So it doesn't, depending on how thin you make them, you can actually achieve that breakdown at a much smaller absolute voltage. Sorry, I didn't put my labels in here. Does that make sense? Okay, so it's just a matter of overcoming the distance with a high energy. So, and what happens is, then these are diodes, right? So photoluminescence, we talked about was just an intrinsic semiconductor, but LEDs really are diodes, light emitting diodes, right? That LED, that light that's given off, you get blue, happens right here. My electron hole pair recombine, right? The electrons in the valence in the conduction band, the holes down here. That electron gives off energy, right? When it recombines, and so that energy can come off as a wavelength, as a photon. So LEDs are diodes in which this emission, the energy here, is given off in a particular focused, narrow focused, in narrow frequency bands. There's a specific energy associated with this. As we already talked about in the energy diagrams, there's a very specific energy gap that we're covering there. That energy gap corresponds to a particular wavelength. So when a blue LED, then you've got to have something with a high energy gap, a diode with a high energy gap. And so they are trying to remember what crying out loud. What are the blue ones? What are blue LEDs, Mr. I can look it up on the internet faster than Steckmeyer can remember it.
Doping of GAN.
Gallium nitride. There you go, gallium nitride. That's what I wanted. So if you look in your nitrogen is a group 5 and gallium is a group 3. So you dope gallium. You do gallium arsenide. It's red. Gallium arsenide, energy gap is red. Gallium arsenide, a mixture of gallium arsenide and phosphorus. Gallium and arsenic and phosphorus is green. Gallium nitride is the blue. So it just depends on which particular combination of materials you have, yes.
Does this have anything to do with how fireworks are made too? Or?
Completely thrown in there. That's a chemical thing.
That's chemical, okay.
Yeah, ask Dr.
Upstairs,
Doctor upstairs?
Dr. upstairs, sure.
Dr. Hannon?
Dr. Smartcar for that.
Oh,
Dr. Kroll. I'm assuming that's who you have for chemistry, right?
okay. I took it in.
You took it out there?
Yeah,
Okay. Okay, so we can also look at the same effect. Oh crap, I want to talk about transistors first. I'll come back and talk about the energy levels of diodes if we have time. But I want to make sure we at least have a discussion of transistors. Okay, so the transistor, so this is an NP or PN, this is a diode. That's just two materials. Transistors either come in PNP or NPN form. And it turns out back here, I should have mentioned this. N to P, the number of electrons participating in this process here, crossing the junction, is proportional to E to the V over B, where B is some kind of a constant and V is the applied voltage.
Is B the thermal voltage?
So, right, it would be. Right. But for our purposes, it's just a constant. It's just a fixed value. So with a transistor now, I'm going to do an NPN since we did an NP there. So this is an NPN transistor. So we have N's and two N's and P's in the middle. And what we do forward bias on one of the junctions and a reverse bias on the other one, like that.
Is that like 3 batteries?
What's that?
That, like,
This is a battery. This is a voltage source. A battery, by definition, is the combination of multiple voltage sources. It's a battery of sources. Does that make sense? No, it's really, I mean, that's where the name battery came from. That's where the,
Legions.
yeah, okay. Could have called it a legion, but I guess,
Missed opportunity.
anyway. Okay, so we have 2 junctions here, and again, we've got the, and then, like that, right? Until it's energized. So when I energize it, what's going to happen? Well, what's going to happen to all these negative charges on the left side? They'll go to the middle, right? They'll go this direction. What about all the negative charges over here? Right, so once I charge it, once I apply the voltage, once I close the switch, right, these all kind of congregate over here. These try to congregate here, but perhaps less densely, right? And the red, the holes kind of move, the holes kind of hang out really. I mean, it's all relative, I guess, but anyway. So, but the electrons here are therefore going to want to come in here and recombine with holes, right? Because they have a forward voltage. So this one has no conduction, right? On junction 2, there's no conduction across junction 2. So the immediate thought is, okay, these electrons are going to come in here, and basically we get conductivity happening over here on this side, but nothing happening over here, right? But if this is a thin region, right here, or if the likelihood, the recombination time is, excuse me, is small enough, some of these electrons are actually going to make it through to the other side. Right? Because they have a thin region here, they don't hit anything, they don't happen to bump into a hole they can recombine with, boom, they make it through to the other side. As soon as they make it to this side, what's going to happen to them? They go, phew, right? Right? So I've created conductivity, and they're extras. Right? They make it over here, they're extras, so boom, they can make it out and around. Right? So the current flowing in this side then some I naught e to the v e over b, because the number of electrons participating in the conduction process is proportional to VE, right? Saw down there. So there's going to be some proportionality of those. I naught takes into account the fact that the thinness of the P, whatever, some annihilation does occur here. But then it's E to the VB to the rest of it.
Isn't one of the ends more highly doped than the other?
Is one of the ends more highly doped than the other? So.
Because there's polarity in NPN and PNP transistors.
Yeah, and I'm trying to think which one would be the more highly doped. I'm thinking the one on the left would be more highly doped, but I'm not certain of that. But the point is, in doing this, because some of them are annihilated, so I'm saying, I think this is more highly doped in order to overcome those that are annihilated. But nonetheless, the point is, you get an output response current in the output circuit that depends on the voltage of the input itself. Which is the purpose of the transistor. Get a small change in VE to become a large change in IC. Okay. Now, that's a conventional PNP or NPN. You can actually use this, you can actually do this with just the diode that we have over here too. Okay, so we have this depletion zone in the center for this thing that's under reverse bias. Does that make sense? Yes?
I have a question over here. Is that a VE or a VC?
That's a VE, and the circled thing is a VE. Because VE is what controls the number of electrons at junction 1. Right? It's this voltage, the junction 1 voltage, that controls the number of electrons crossing that gap. And therefore, a percentage of those will make it all the way over. Okay. All right. So now what we're going to do here is we're going to sort of take this reversed NPN, or NP junction, and we're going to apply an additional constraint here. So actually I'm going to make this bigger. So now what I've done is I've made my points of contact just on the surfaces here of the center section. Okay. So I have this depletion zone in the center, and then what I create up here are two more contacts on this side. And there's some kind of a circuit up there. Okay? And then this is the VI, the input voltage. So what happens is, as I change my input voltage, I change the size, the relative size of this conduction zone. Does that make sense? As I increase the voltage here, I shrink these guys down to a narrow, I increase the charge density in this region. Okay? So that I can get conduction between my source and my drain. Sense? See what's happening there? So basically, if I apply a small bias here, then the charge density here is very small, and I get very little conductivity through this thing. But as I increase VI, I get more and more conductivity through here because I increase the charge density in the region between the source and the drain. I make this more like a wire between the source and the drain. Does that make sense?
So I'm guessing that for a better transistor, that transition is faster and sharper than for like more abrupt for
Faster and sharper. What do you mean by faster? I'm not sure I understand.
a sharper transition.
Oh, between conduction
Right,
and not
It
conduction?
doesn't like, well, you turn on VI and like it gets more and more conductive gradually. It's like, it's more of a sharp.
I see what you're saying. Yeah. Yeah, it's not sharp in any case. I mean, it's a continuous function. It's not, on and off are not, it's not a square wave anywhere.
Right.
Right.
But a more
But-
ideal transistor would be.
So an ideal transistor, right, would be right. So you want to get something that's more and more ideal, yes. But and you can do this with NPN. Yeah, I can do the same thing here on the NPN, where let me look at this from the side. I'm going to take this thing and sort of rotate it up from the side. So I have my N zone, my N here, my P there, and my N there. Okay, so this is N, P, and N. And what I end up doing is I end up putting a an insulating layer here, SiO2, so it's just glass. And then there's a point of contact over here. This would be, I'm going to do source on this side. And then my drain is going to be here. Okay? Does that make sense? So this is all conductive. The SiO2 is insulating. Does that make sense? And then what I do is I put a gate in here. So if I positively charge my, actually I'm going to erase that. This is the gate. If I put a positive charge on my gate, then I'm going to take all these holes in P and scare them away. And I'll end up with just a few negative charges up here at the top. So my drain is positive, my source is negative, right? So I have an N-type semiconductor up here, so I have a bunch of negative charges in each of these. So the idea here is to be able to allow a path for negative conduction through this region, for the electrons to move through that region. The current would obviously be moving the other direction. So by applying this positive charge, I can turn on and off the switch between the source and drain. Though there are predominantly positive charge carriers in this section, there are still electrons there. I scare the positive charges away, I end up with the electrons up the top. Okay, and just create, again, a narrow path for turning it on. These are both of these two are called field effect transistors, because it's the electric field applied by the gate that causes the conduction to occur, that allows the conduction to occur. As opposed to these, where it's not about a field redistributing the charges, but rather just getting the charges to cross the gap. Does that make sense? Okay. So, all kind of driven by, I'm 49, I'm not going to get back to it, okay. So I'm not going to be able to go back and explain these from the standpoint of energy levels, but at least you have some kind of an idea where these come from. All right, any questions? Then we'll call it a semester. We'll be, again, no class on Wednesday, and we'll be back here on Friday to answer any questions you have about the exam. And especially if somebody reminds me in the intermediate time, like say tomorrow, I will try to pull together some materials for the electrical top of this section sort of for review. But the other things are the same. Yeah.
Hey, can you pull some things together?
Yeah.
Dang it!
In the MOSFET, isn't it the